So today we're going to be evaluating a function. Now, we all know how to do the math in what we're doing today. The actual algebra isn't too difficult. It's mostly just arithmetic, but what we're doing is we're figuring out how to read a function. Now, the way a function is written is what we say f of an input equals the output. Now, the f is the name of the function, so this is the function name. The input generally is a variable that we show some sort of number, and it says, hey, I'm going to place this number as the variable. Then this is the operation. This is the thing that we do to get the output. Cool. So let's take a look at what that actually means in practice. So if I have f of 2 equals x cubed, what that means is that I'm going to take this function called f, and first off, I don't touch the left-hand side. With functions, this is not f times 2. This is saying my function, I'm going to go plug in a 2. So what I do is I go to the right-hand side and I say, hey, wherever I see a variable, plug that in. Well, I see a variable right there. So what I'm going to do is I'm going to say, hey, plug in a 2. And now what I tend to do is I like to put parentheses around it because it's going to stop us from making some very simple mistakes. I have f of 2 equals 2 cubed. If we remember that 2 cubed is actually equal to 2 times 2 times 2, 1, 2, 3 times. If we had something like 2 to the 5th, that would be 1, 2, 3, 4, 5. We're multiplying it times itself that many times. So 2 cubed is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So my f of 2 is equal to 8. Boom. And that's it. Apologize for the noise. They're mowing the lawn outside. And just like that, it might get a little loud from time to time. But we're going to push forward. So one of the reasons why I put parentheses around my input, or the parentheses around my variable input, is because of times like this. If I notice that I have my f of -4, and I'm plugging that -4 into everywhere where I see a y, well, I would put 4, and I would put parenthesis -4 minus 21. And I'd automatically know that, okay, with parentheses, I'm distributing that 4 inside. 4 times -4 is going to give me a -16 minus 21, which is going to give me a -37. Now, that seems pretty straightforward, but let's see what would happen if I didn't actually put parentheses. What might you be tempted to do? Well, what a lot of students will do is they'll say, okay, f of -4 is equal to 4 -4 minus 21. And they plugged in the -4 just like that. What you might read that, did they plug it in correctly? Kind of, sort of. But because they didn't put parentheses around their 4, it looks like I'm taking 4 minus 4. I'm no longer multiplying, all of a sudden I'm subtracting. And we can't change operations like that willy-nilly. So I put parentheses around it to stop us from making mistakes like this. Let's go ahead and let's not do it that way. And another one of the things that we have is that with a function, it doesn't matter how many times I see the variable. If we notice here, I have a variable twice. I'm going to plug -10 into each one of those. So what I'm going to do is I'm going to take a -10 and I'm going to square it plus 9 times -10. So my f of -10 is equivalent to this. Now another rule, if I take this and I say, okay, I'm squaring this, we remember that that's -10 times -10, which is going to net us a positive 100 minus 90. Again, a common mistake is that students will forget about that negative and they'll say, well, -10 squared is -100. No, it is a positive 100. And if I subtract 90 from it, I get plain old 10. Boom. Only a few left. If I take f of 3 if I look right here, okay? So I'm going to say f of 3. I'm going to take my negative sign, and again, simply by putting in a set of parentheses, I almost made that 3 negative on accident, I catch myself from making very common and very easy mistakes. When I put the parentheses in here, it made it abundantly obvious that I'm going to square this and then make it negative. Remember, we follow order of operations. 3 squared is 9, and then I make it a negative 9, minus 16 times 3. Then I say, okay, negative 9, negative 6 times 3 is negative 48, which is going to net me a negative 57. Again, a very common mistake is that students will forget about that negative, or they'll try and push that negative in there and square a negative 3, and they'll get a positive 9. Make sure that when we put parentheses in, that helps us follow order of operations. Let's try one that is a little more common of a mistake, because what happens if there's a negative and a negative? This is another mistake that students often make. Now, this is going to be the same problem. Instead of inputting a positive value, we're inputting a negative value. So I have an f of negative 2. And in this case, I'm plugging in a negative into a negative. And we all know that a negative times a negative is a positive, right? Awesome. So what the students will do is they'll say, well, this is already negative. When I go to square that, shouldn't I just ignore it? Or wouldn't that make it a positive 2 squared? Well, not necessarily. Remember, we're going to perform order of operations first. So I square the negative 2, which makes that a positive 4. And then I apply that negative and I distribute it in. So negative times 4 is negative 4. 11 times negative 2 is negative 22, which gets me a negative 26. Awesome. And so the last one, just to make sure that we know how to do the same thing with fractions, and kind of a set of fraction review, we got this one. So go ahead, pause the video for just a moment, try this one, and see if you get the same answer. Okay, so let's take a look. Plugging in the negative 3 halves, I'm going to get 4, negative 3 halves. I'm going to square that, plus 8 times negative 3 halves. And so what I get is anytime I square something, remember, I'm writing it out twice. Negative 3 times negative 3, 2 times 2. Another way to see this is if I take negative 3 halves and I square it, negative 3 halves, negative 3 halves. Well, negative 3 times negative 3 is actually negative 3 squared. 2 times 2 is actually 2 squared. So I get to square each number. So negative 3 times negative 3 is going to get me a positive 9 fourths. Plus, okay, and if I do this, I get negative 24 all over 2. And if we remember, we have a shortcut that we can do here. If I take 9, multiply by 4, and divide by 4, we can do what we call cross-reducing. And what is cross-reducing? Well, cross-reducing is saying that if I were to perform this operation, and I were to take 4, put it over 1, and multiply it by 9 over 4, well, that's 4 times 9, which is the same thing as 9 times 4, correct? Nothing has changed. And what does 4 over 4 do? Well, 4 over 4 reduces, which is what we call cross-reduction. If I were to swap the order of which I wrote some of these things in, as long as they're all connected via multiplication or division, I can go ahead and change the order, cancel them out. Which leaves me with 9 minus 12, which is a negative 3. There we go. Boom. Okay, so today what we're doing is we're evaluating a function, but we're evaluating a function in a piecewise format. And now, this is important. It's not really much more difficult than what we did previously, but the idea is that we have domain restrictions listed after each piece. So typically what you would do is you would say, hey, I'm going to take this and I'm going to plug in my 5. And what we did the other day was we said plug 5 in wherever we see an x. You'd say, okay, f of 5 is equal to bracket 1/2 of 5 and negative 5. And we'd pause and we'd say, hey, hold on. I'm about to get 2 answers. And I know I cannot call it a function if I get 2 answers. For every 1 input, I must get 1 output. In this, I'm plugging in 1 thing and getting 2 things back. Well, let's see what's going on. Well, for here, I can only plug in values that are less than negative 2. And for this bottom one, I can only plug in values greater than or equal to negative 2. So I have to do what I call checking the domain. So check the domain. Is 5 less than negative 2? No, it's not. So 5 is not less than negative 2, which means I am not going to use the top portion. Is 5 greater than or equal to negative 2? Yes. So I'm going to plug my 5 in to the bottom, which means that my function is as simple as saying, what is negative 5? Well, f of 5 is negative 5. Boom. And there we go. I don't plug it into everything. I only plug it in where appropriate, and then I ignore everything else. So with this one, I only plug it in where appropriate. If I go and check, negative 1 is less than 2, so I'm going to be using that function. Negative 1 is not greater than or equal to negative 2. I'm not going to be using the bottom function. So I'm going to take my f of negative 1, and I get 7 absolute value of negative 1. 7 times 1, which is a positive 7. Boom. And there we go. And remember, we don't actually touch the left-hand side of the equation because that is the name of the function and what we plugged in. This isn't actually performing any operations over there. Works the same with fractions. I'm going to check the domain and see 5/4 where it falls. Well, remember 5/4 is just over 1. It's actually like 1.25. So I'm going to check, okay, good, these are negatives. 1.25 is not less than that. So I'm not going to plug it into the top one. I can, apparently, I can plug it into the bottom one. Decided to cut my yes off early there. F of 5/4 is equal to negative 48. Open up a set of parentheses, 5/4 squared. And what we covered yesterday, we remember the fact that if I square a fraction, I'm squaring the top and squaring the bottom. So 5 squared is 48 times 25, and 4 squared is 16. The other thing we also covered about cross reduction is that I can write this whatever way I want. If I want to write it as negative 48 over 16 times 25 over 1 and just swap the bottom 2 numbers, well, then that allows me to take 48 and divide it by 16, which I know is just a plain old negative 3. So I'd end up with a negative 3 over 1 times 25 over 1. Which makes that a negative 75. Boom. And there we go. So let's try a few more that might have some complexities to them. Now, when we deal with square roots, if we remember, square roots are going to give us 2 possible answers. So I'm going to check the domain, and I'm going to say, where does 3 fall? It's not less than negative 3. is between these two, so I can use that one, but it's not greater than 4. So I must be using the middle one. And so what I end up with is the square root of 3 times 3. The square root of 3 times 3 is going to be the square root of 9. And so when I say what is the square root of 9, well, what two numbers multiply to give me 9? And most of us say 3. And that does equal a positive 9, but there's another two sets of numbers, a negative 3, which will also equal a positive 9. They both equal the same thing. So when I take the square root of 9, I give it both the positive and negative 3. So I actually get two answers. Perfect. So let's go ahead and let's take a look at this. So f of 0. I check my domain. 0 is not less than negative 5. 0 is between these two. And 0 is not greater than 1. I'm going to plug in my 0. It's 2 over 0. And we run into a problem. I can't plug 2 into nothing. So what we say is that when we try and plug 2 into something that doesn't exist, this function is actually undefined. And we'll go over later in rational equations what ends up happening here, because we actually do start approaching at least one number. In this case, we're going to approach two different numbers, which is why it's undefined. We're looking at some sort of dimensional constraint that we can't overcome simply with a 2. So we'll get back to that one later on. And the last thing that you might see is if I check my domain and I see a 1, I notice the fact that 2 of my domain restrictions have a 1. First off, it's not less than negative 3. But I really have to check my signage because it is included in this one. 1 is less than or equal to 1, which means I'm going to be using the middle one. Common mistake might be to plug it into both of these, but 1 is not greater than 1. It is almost, so almost, but no. That one's just a flat no. So I can plug it into the middle one. F of 1 is equal to the absolute value of 1 plus 1. So f of 1 is equal to 1 plus 1. F of 1 is equal to 2. Boom. There we go. And that's it. So today we're being graphing with a graph with a limited domain. Now, a domain limitation means that I'm going to give my graph a starting point and an ending point, typically shown what looks like what commonly can be perceived as a coordinate, but with a domain limitation, it's saying, hey, I only am caring about the values, what the graph looks like between these 2 points. And now, because it is domain, we're looking at the x values. So I'm saying between what 2 points. I'm not asking between what 2 coordinates. Now, today we're showing this with interval notation. And an interval notation means on the actual border, if I want to include that point, I'm going to put that number in brackets, like shown right here. I'm going to include the negative 4 and include the 2. If I don't want to include it, I'm going to include parentheses, just like what I see right here. I'm not including that point, and I'm not including that point. So let's see how this is done. Now what I would do, I typically graph these with a pencil first off, so that I can erase the portions of the graph that I don't need. Because again, we're only concerned with part of the graph. So I'm going to graph this. This is a standard line. I have an intercept at positive 1, and I go up 3 and over 4, down 3 and back 4. Now that's going to give me a straight line just like this. And again, I'm drawing this very lightly because I'm going to be erasing this here in just a moment. Now, the other thing is I'm only concerning myself from -4 to +4. So what's going to happen is I'm literally going to say, okay, from -4, 1, 2, 3, 4, I'm going to erase everything on the outside. I don't care about that portion of the graph, so I'm going to erase it. And I'm only going to go to +4, which means I'm going to take this and move it over 1, 2, 3, 4. That means I don't care about anything over here. I'm going to erase it. Boom. So that's the only portion of my graph that I want to keep. And then am I going to include the -4? No. So I'm going to put an open circle. Am I going to include the +4? No. It's going to be an open circle. So what I end up getting is this is my equation. It goes from this point, increases at a rate of 3/4 and stops right there. Done. So let's try it with included points this time. So again, I'm going to start out with a pencil so that I can erase it. See, I'm going to start at -1. I'm going to go down 1 and over 2, up 1 and back 2, and I'm going to connect them with a solid line. Again, I'm drawing this very lightly because I'm going to be erasing a good bit of the graph. The next thing is I'm saying at -4, I don't want anything before that. That's my starting point. So I'm going to take it and go back 1, 2, 3, 4. I don't want anything over here, so I'm going to erase that little piece of the line. That no longer exists. And then I'm going to go to 2, so I'm going to include the entire graph all the way up until that part. So I'm going to go from 1, 2. So none of that portion of the graph am I going to include. So I'm going to go ahead and I'm going to erase it. So I only have that little piece. This time though, the point at -4, I'm going to include. So I'm going to shade it in. And the point at 2, I'm going to shade in, and I'm going to shade in the entire line given my domain restriction. So boom, I have a line segment with a start and a finish from -4 to 2. So why don't you pause the video, try and do this one on your own, and then resume play once you've finished. Okay, so let's take a look at this. I'm going to pull out my pencil. This is a line with no y-intercept. So it starts here, up 2 over 1, up 2 over 1. I go down 2, back 1, down 2, back 1. I'm going to connect this with a solid line. Draw it very lightly so that I can erase it later on. And now, one of the things that I notice when I start with my domain restriction at -3, -1, -2, -3, I don't have any graph here, which is going to present a problem because if I want to see where the graph is given this domain restriction, I can't see it. So I'm going to have to change my scale. So I'm going to scale this graph by 2. So my y is each by 2, and my x is by 2. And what you might ask is, well, wait, wouldn't that change how the graph is shaped? No. If I change the scale of both, this is a straight line, it's going to continue to be a straight line. Instead of going up 2 over 1, up 2 over 1, up 2 over 1, I still hit the same point by going up 4 over 2. Because we remember that 2 over 1 is equal to 4 over 2. So the slope looks the same. But what it allows me to do is that it allows me to get that -3 on the graph. So 2.5 blocks, 1.5 blocks is going to get me that -3. And so I'm going to erase everything before that. It's going to give me a point right there. And then I'm going to go over 1, which is going to be half a block, and I'm going to erase everything over here. So all the way up to right at half, right there. So now at -3, I have a point right there. At 1, I have a point right there. I'm going to connect them. So it's only that little piece of the graph, and I'm going to include when I hit this boundary. Done. This boundary is not included. There we go. So now, does domain restrictions only work for lines? Well, let's give an absolute value a shot and see what we notice. So I know this is the parent absolute value function, which is going to give me a straight diagonal line and a straight diagonal line in both directions. Again, I'm not going to draw it very dark because I'm going to be erasing it. I know I'm only going to be including it from -4. So 1, 2, 3, 4, and I will erase it. Erase that little piece. There we go. And I'm going to stop at 2, so I'm going to take it and go 1, 2. And I'm going to erase all that. That no longer exists. I cut it off the graph. And so my graph this time goes from here to here with only the left point included. So I'm going to go ahead and trace over my graph for the actual portion of the graph that I'm going to keep and shade in that point. Done. So the only way that this could possibly get any more complicated is what happens if we have an infinity? Well, let's think about that. So my starting point is at 0, and my ending point is at infinity. It sounds like the graph is going to have a start, and can we ever actually reach infinity? No. So are we ever actually going to end the graph? Also no. Perfect. So let's go ahead and let's graph this. I know that inside the brackets, that's going to be a right movement. So I'm going to take that V and shift it to the right by 2 units. The slope remains unaffected. It's still a perfect diagonal. But we notice that the parent graph has been shifted to the right by 2. And then the next thing, I'm going to start at 0, which means on the origin, I'm not going to include the left hand. None of this is included in the graph. Let's go ahead and erase all of it. Nothing before that line. But the graph does continue to the right, and in fact, it never stops. So if I put my circle, I'm going to shade in this portion of the line, and because it doesn't stop, remember, we just have to end the graph with an arrow which says, hey, this graph continues in that direction. Perfect. My 0 point is not included. Okay. And for the next one, what happens if I don't have a starting point, but I have an ending point? Let's take a look. This absolute value function has been shifted down by 3. So I know 1, 2, 3 starts right here. And that 3 in front of it means that this is the slope to the right. So I'm going to say, okay, the slope to the right is up 3 over 1, up 3 over 1, up 3 over 1. And then I'm going to mirror that on the other side. Up 3 left 1, up 3 left 1. I'm not going to continue down because the absolute value does bounce. It does have a V shape, which is going to allow me to do this. Has a V there. Has a V right there. Cool. So again, I'm drawing this very lightly because I'm going to be erasing, well, I'm not going to be erasing anything over here, but I am going to stop at 1, which means none of this gets included. So let's go ahead and erase all. this hard work we did over here. Turns out this was for naught. So anything after 1 just gets erased. Which means that my point at 1, I have the bottom of the V, and goes up, 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 and away, and continues on by putting an arrow. Now that 1 point I actually included. There we go. Now, the last thing I might ask before we end is, can we actually have, can we have an interval such as -infinity to 1, or like we did on the upper one, let's say 0 to infinity? Can we actually include infinity in our interval? Can this happen? Think about that. When we have the brackets, that means we include the point. So we go all the way up to that point, and that's part of our graph. You're going to ask yourself, can you actually trace the graph to infinity? If your answer is no, then we cannot include. No. Infinity is unreachable, and so is its point. Because infinity is unreachable, we cannot include graphs like this. It does not work. Infinity always has to be a parenthesis because, again, infinity is something we could never reach. And that's all we got. So today we're doing a rather simple exercise, and we're going to be graphing graphs with limited ranges. And now, one of the things that we want to notice is that when we limit a range, and we limit any graph, we're probably going to want to draw it in pencil because we're going to be doing some erasing. But furthermore, a range limitation has a minimum point and a maximum point. What a lot of people like to call, let's call this a floor and a ceiling. So we have a floor and a ceiling. Now, these almost are always because of some limitation in the cause and not the cause itself. So a good way to look at this is by saying, hey, my Geiger counter has an upper limit. It has no effect on the graph, no effect on the actual radiation, but my Geiger counter can only record up to a certain range and then the graph quits. And so that's why we say there's a ceiling. And it's a limitation of the technology and not the actual cause of what you're trying to measure. Furthermore, when we look at limited ranges, one of the things we'll eventually go through is in calculus, you're going to be looking at what we call limits. And so when a graph starts to spiral upward, so let's take a look at, if I were to draw just a sample graph and say, hey, my graph is going up, 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 but it's starting to taper off. At some point, that graph is going to flatten out. So after some amount of time, where is the point where we can assume that that graph is flat? And we're going to say, okay, that graph flattens out at some y value. What is that y value? And that's basically once we get to infinity. Right now, we're not dealing with curves, we're dealing with straight lines, but the concept is eventually we will get to some sort of limited range. So let's jump into this. So we recommended that we graph this in pencil because we are going to be doing a good bit of erasing. So when we start, we're going to say, okay, I have a line of y equals negative 6x plus 2. Go down 6, 2, 4, 6. Wait, 2, 4, 6, yep, over 1. So I have a graph that looks like this. Let me grab my ruler. So I have a graph that goes all the way up and all the way down, but I only care about values where y is less than 4. And so one of the things that you don't need to do is you don't need to draw the limit itself. You don't need to draw the boundary, but I've noticed that students tend to get a very good image of what's going on with the boundary. If I say y must be less than 4, I'm only looking at values down here. I am no longer dealing with any values that are greater than 4. So I'm going to get rid of this. And that goes away. Might need a no eraser. The only part of the graph that we keep is this lower part down here. So we have our line. Now the boundary itself is an open circle because I'm not actually including the boundary. Y is less than 4, not equal to 4. So there's our graph. We have another one. So also to use our terminology, that would be a ceiling. It can't go above that, it's stopping. This one's gonna be a floor. So if I take my line and I say, okay, start my point at -1, and I go up 2 over 3, down 2, back 3, I get a line that looks like this. Right there. But again, I'm only concerned with the values that are greater than -4. So what I'm going to do is I'm going to say, hey, only greater than -4. Only those. I don't want any values below -4. So I don't want this little piece of the graph. So I'm going to erase it. And again, what I've said a lot of students seem to enjoy doing is they enjoy putting a barrier. Y must be greater than or equal to -4. Now, the thing that I think about the barrier is that it should be a solid line. For some reason, a lot of students like to draw a dotted line no matter where the barrier is. I think because they know that it doesn't need to be drawn. But in this case, I'm going to go ahead and I'm going to draw it all the way. We erase the part below there. I'm only concerned with the part of the line that's above that barrier. And I'm actually going to include the barrier itself, which is why I like to draw a solid line. It shows me that it starts here and goes up. And there we go. And the last type is what happens if I don't have just the floor or just the ceiling? What happens if I have both? Well, it's no big deal. We graph it like we always would. I put a point at -1, and I have a slope that goes up 1 over 1. And so it's a perfect diagonal. Let's go ahead and get this drawn. Perfect. But now what I'm going to do is I'm going to say, hey, I'm only dealing with y's that are greater than -2, which means anything -1, -2, anything down here, I'm cutting it off. And at the same time, y must be less than 5. So I'm going to come up here and say, hey, 1, 2, 3, 4, 5. I actually don't even see it. So unfortunately, what I'm going to have to do is I'm going to have to start over on this because I can't see the barrier. You might be able to keep going because you might have a graph with more than 5 spaces. I'm going to have to start all the way over. So I'm going to say, hey, my graph is by 2s. Which means I start right here. Oh, doing that in pen. I'm not going to be able to erase if I keep doing that. There we go. Got my line. I'm going to erase anything below -2, which in this case is a lot higher up. Because in this case, my barrier, y must be greater than -2. And then I have another barrier at 2, 4, 5. Y must be less than 5. So I'm going to have to erase everything above that barrier, which is going to leave me with a very limited graph. It's between -2 and 5, neither of which is included. That's all the graph that I have. That's it. So, the question that you might ask yourself is, does that logic work with other graphs? What about an absolute value? And the answer is, yeah, it does. So with an absolute value, I know this absolute value has been shifted down 4, so 1, 2, 3, 4, and I have a perfect diagonal going up over here, and a perfect diagonal going up over there, but I'm only going to deal with y values greater than -2. So what I'm going to do is I'm going to say, hey, y must be greater than -2, which means I'm only dealing with values above that. So I'm only going to deal with this piece over here and this piece over here. I'm not actually going to include the barrier, so both times I'm going to include open circles, and I'm just going to go ahead and get rid of this lower piece down here. So does it work for an absolute value? Of course it does. You're just going to get 2 pieces. You might not realize it's an absolute value, because what happens if I only get that little pointy piece? Well, no big deal. Just take off the part of the graph that doesn't work. This is an absolute value that's been shifted to the left 2, so 1, 2, and it opens downward. Although I notice that because I have a -3, that may or may not fit on my graph, so I'm going to go ahead and preemptively make this graph by 2s. And I'm going to say, hey, left 2, and it opens down. Don't need to draw that thick. I'm going to be erasing a lot of this. So in this case, y has to be less than -3. Draw my barrier right here. Y must be less than or equal to -3, which means that I'm only dealing with the lower portion of this graph. Perfect. And I'm actually going to include my 2 points. And so this little piece right here, don't need it anymore. That is a part of the graph that is greater than -3. We don't care, we don't want it. Perfect. And so our last example is an absolute value that has both a floor and a ceiling. So again, I see that I have a value at -5, so I'm going to do these by 2s. This just allows me to fit everything I need onto the graph. So up 1, I go down 2 over 1, and I go ahead, and when I graph this, because I'm graphing at in-between points, I have that. I'm going to say I want it between -5 and 0. So 2, 4, 5. So y must be greater than or equal to -5. It's got to be bigger than that line. And y must be less than or equal to 0. Which means that I don't have the point, but I also don't have these extended lines all the way down to forever. I have what looks like 2 line segments that are on a collision course. Get rid of the unnecessary parts of my graph. I don't need the vertex, I don't need those legs. And there we go. That's how we graph an absolute value with a floor and with a ceiling. So today what we're doing is we're going to be graphing a system of equations. One of the big things we've spent the past several parts on is how to graph a line and how to graph several other types of lines, so that when we look at a system of equations, we're solid on that front. And a system is basically just when 2 or more equations cross paths. A solution is the point or points where they cross. And we'll see what a solution means mathematically as well as visually. Visually, it's very straightforward. So let's take a look at visually. This is going to be a diagonal line. I have a point at 1, and I'm going to go up 2 over 5, down 2, back 5, and I'm going to graph this line. And so I have my y equals 2/5 x plus 1. You always want to label your lines because when you start graphing big systems and you have lots of lines, you want to see which one is which. You don't want to have the reader of your graph, the person who's looking at this, get confused as, well, which one is this? Because it just looks like a bunch of lines. This one is going to be a horizontal line. At y equals 3. And so the solution is literally just finding that point where they cross. It's right there. That's at 1, 2, 3, 4, 5, 1, 2, 3. So at 5, 3, my solution is at 5, 3. Oh. Now, what this means when this is a solution where they cross, technically what I could do is I could take each of the equations. I could say, okay, if I take y equals 2/5 x plus 1 and I plug in that point of 5, 3, that would mean I would have 3 equals 2/5 of 5 plus 1. 2/5 of 5, my 5's cancel out. So 3 equals 2 plus 1. 3 equals 3. That works. That's a solution for that. The other aspect is I plug into the other one. So if I have my y equals 3, well, I plug in, I don't need an x, I just need my y. So does 3 equal 3? Yes, that's a solution for this one as well. So that point, 5, 3, works for both equations. That's what it means mathematically to find the solution. The number that makes both equations true. So, not too bad. Does it work differently for lines like this? No, it works exactly the same. So let's plug a point at 1. If I have a slope of up 2 over 1, I have my graph of y equals 2x plus 1 right there in blue. And then in green, I have y equals 2, and I go down 1 over 1. And so if I graph this, well, I have this line of y equals negative x plus 2. And now, a lot of you might see the number one problems that we have with graphing equations is my solution right here isn't on any grid mark. So we're going to have to take a guess. 0.5, 1.5. That may be accurate, it may not be. Depending on how we know these numbers work, which we'll cover in a later section, this is not going to be at. This time we know our solution is only near what looks like 0.5, 1.5. That may be our answer, but then again, it may not be. So we're going to have to find a method in a later section on how to find when our answer doesn't fall directly on a grid like it did earlier. So the number one thing with any system of equations is most of the time we just want to be able to see what's going on. So two ways to graph this. We can either use our x and our y intercepts by covering up the y, solving for x, covering up the x and solving for y. If we don't remember how to do that, all we're going to have to do is solve for y. So let's subtract our x and divide everything by 7. And let's graph that. So 3, if I have a slope of -1, right there. And over here I have a -8x plus 4y equals -12. Actually, I should have been doing that in green. I'm going to save my solution for red. I'm going to add my 8x, so 4y equals 8x minus 12. Divide everything by 4, 2x minus 3. So up 2 over 1. Let's see. Boom. And so what we notice is that our solution, albeit it looks like it's right on that point, we're not really sure is our graph a little off? Is it actually off a little bit? Unless we actually count. Now this one we know actually is going to fall on the number 2, 1, just because my graph is a little sloppy. But oftentimes, especially when it comes to these half points, you just don't know. Unless you are a very precise grapher, especially if this intercept is way off of the x and the y-axis, you may not know exactly where your lines cross. And so this time, I'm going to actually say the solution is at 2, 1. That's the drawback in graphing, is that oftentimes, while these graphs give you a good image of the overall picture, when you zoom in on the finer details, it's not so clear. So let's try one more with lines before we jump off to something else. So with this, what you might recognize is that this is a specific formula that will make your life very easy if you remember how to graph it. If not, you're going to have to isolate your y and graph it. So pause the video, try and solve this, and see if you can't solve it faster than isolating the y. Okay? Let's take a look and see how you did. Now, we know that this is actually going to be in what we call point slope format, which is going to be in something called y minus y1 equals m times x minus x1. And what's so special about this is the fact that our y1 and our x1 are shown. We have a point at x1, comma, y1. And then our m right here is our slope. So no worries, if you didn't know that, this would make your life easier. Let's go ahead and do it the long way, and I'll show you where that comes from. So y minus 3, I'm going to go ahead and distribute my 1/3. So I get a 1/3 x minus 5/3. I'm going to go ahead and I'm going to, let's see, I'm going to do this in, let's do this in pink. And I'm going to add 3. But I'm going to add 3 over here, but I need it to be in thirds. So 3 I know is equal to 9/3. So I'm actually going to add 9/3 over there, which is going to give me y equals 1/3 x. 9 minus 5 is 4/3. So there's my graph. And so when I graph this, 4/3 is not very exact on the graph. So I'm going to go up 1 and over 1, 2, 3. There we go. I get that. And on my other one, I'm going to do the same thing. So I have a y minus 2. I'm going to go ahead and distribute that 2/3, negative 2/3 x plus 4/3. And now here I'm going to add my 2. But over here I'm going to make my 2, which is actually 6/3. I'm going to add 6/3 over here. And so that's going to give me 10/3, which is just over 3. So I get a number right here. And I'm going to go down 2, so 1, 2, and over 3. So let's take a look. Perfect. And we see our solution is right here, 2, 2. And now this is if you had to actually go and isolate the y so that you could graph it. Now remember though, this is in point slope format. So the shortcut is the fact that I could have just graphed a point, let me do this in purple, at my x value, which is 5, 3. So I could go over and say 5, oop, that's directly on my line. My slope is 1/3, so I can't go up 1/3, so I'd have to go down 1 and, yep. I can just look at that equation, I don't need to do any math, and just graph it. The other one right here is I'm gonna look at these points and say, okay, I have a point at 2, 2 on my green line, and I go down to over 3, which is also on my green line. So if you know how to read point slope, it's gonna make your life a lot easier. So that works well. Now, what happens if I don't have just lines? What happens if I have something like an absolute value? Well, let's take a look. This one is an absolute value that's been shifted up by 2. So I have a graph and a graph, and I have a horizontal line right here. So I have y equals 4, and then over here I have my y equals absolute value of x plus 2. This is going to give me not 1, but 2 points. And so this is an interesting subject that we're going to cover later on. With 2 lines, I either get 1 if I have parallel lines. I know those lines will never touch, so there will be no solutions. Or if my lines are on top of each other, I'll have infinite solutions because they're the same line. But those are the only 3 answers I can get. But if I bend the line, I can get a second answer. And what we'll study later on when we study polynomials is that for each bend, I'm adding another solution. So my -2, 4, and my 2, 4. Every time I bend the line, this absolute value has 1 bend, I add 1 solution. So 1 became 2. There we go. And last but not least, let's go ahead and try this one. I want you to pause the video, give this one a shot, and see if you can solve it. Okay, so let's see what you got. This one is an absolute value that's moved down and has a slope of -2/1. So I have something right there. I have a slope of down 2/1. So y equals -2, absolute value of x minus 1. There we go. And now the shortcut way is to look at this and say, okay, I have a point at 1. I know that's actually minus a -3. So I have a point at 1, 3. So let's go to our 1, -3. Oh, it's right there. And a slope of up 2 over 3, down 2, back 3. Ooh. So when I graph my line, I found my 2 points pretty quickly. Y plus 3 equals 2/3 x minus 1. There we go. So I found my 2 solutions right here and right here at -2, -5, and 1, -3. Perfect. Now the long way, if you couldn't spot the fact that I had a -1, -3, and there's my slope, is you just solve for y. Y plus 3 is distribute that 2/3, so 2/3 x minus 2/3. I go ahead and subtract 3. I know 3 is equal to 9/3, so when I subtract 3 on the left, I'm actually going to subtract 9/3 on the right. It's got to be balanced. They're going to look different visually, but they're the same thing. So y is equal to positive 2/3 x minus 11/3, which I know that negative 11/3 is almost 4, so 1, 2, 3, almost 4. And I go up 1, 2 over 1, 2, 3. Yep, that's the same line. And that's how you visually graph a system of equations.